Hello, and welcome to the Class 12 video. In this class, we will be starting our unit on reasoning with generalizations. People make generalizations all the time. I just made one right now. But of course, making generalizations can get you in a lot of trouble. Sometimes people suggest that the way to avoid racism, for instance, is just not to ever make generalizations. But this, of course, won't work. We cannot think without generalizations. So the question is how to do it well. So in this unit, we're going to start out by considering important ideas about arguments that involve generalization. We're going to look at two argument schemes. One where we start without experience. One where we start with experience in the world and draw a generalization from it. That's inductive generalization. And one where we start from a generalization and look at how to apply it to a particular individual or situation. That's instantiation syllogism. As we did in arguments by analogy, each of these two styles of argument will come with an argumentation scheme, which is a specialized version of standard form, and critical questions you should ask to be sure you are avoiding fallacies. We will also look at a crucial and often misunderstood concept that begins to edge us a little bit into the world of statistics, and that's the idea of a correlation. And we're not going to do really much that's scary here, but there's some common misunderstandings about correlation that we need to emphasize. Okay. In the second half of the unit, we're going to look at cognitive biases around generalizations and some thoughts on the social epistemology of generalizations. So Class 15 is cognitive bias and generalization. Class 16 is social bias and the ethics of generalization. But in today's class, we're just going to look at the most basic form of argument associated with generalization, and that is inductive generalization. Inductive generalization is just what you do when you make a generalization. So let's look at it. The first argument scheme we're going to look at is inductive generalization. Inductive generalization is just reasoning from particulars to a generalization. So you start out with statements about particular objects and you wind up with a generalization. A standard example here is the generalization that all swans were white. Europeans, for the longest time, had this idea, a biological generalization, that all swans were white. Then they traveled to Australia and they discovered a black swan. So the generalization turned out to be false. Ever since then, this has been used as a standard example of inductive generalization and how it can go wrong. This slide is just an intuitive visual representation of what is going on with inductive generalization. In the lower part of the side are images of clip art swans that just represent particular experiences. Look, here's a white swan. Here's another white swan. I keep seeing swans, and every time I see them, they are white. And at the bottom, that we have the word particulars. That just represents these particular experiences. The arrow going up represents inductive generalization. And that leads us to the generalization, all swans are white. So the general statement was inferred after having particular experiences with individual swans and discovering that they were all white. We can imagine putting this inference in standard form like this. P1. Of the 100 swans I've seen, 100% have been white. And we really just need that one premise. We could divide it up into 100 separate premises, but that would be tedious. We just say, of the 100 swans I've seen, 100% have been white. Therefore, all swans are white, right? So this is an argument with a single premise and a conclusion. Some preview of terminology here. The 100 swans that I've seen, or that the speaker has seen, we're going to call that the sample, right? Your generalization is always based on a sample. The full statement of the 100 of the 100 swans I've seen, 100% have been white is a particular kind of statement called a quantified categorical statement. So actually, the first thing we need to do in order to understand inductive generalization is understand the kind of statement that we have in the premise. So in this first section, we're just going to look at quantified categorical statements. The best way to get a sense of what a kind of statement is to just look at a bunch of examples. So here are a bunch. All Canadians are humans. Most physicists are smart. Few teachers are rock climbers. No dogs are cats. Some Americans are doctors. Some adults are not forklift certified, right? We call these quantified because they all have words in them that denote how many, right? All Canadians, most, few, no, some, and then some again, except this is actually some are not. We call the words that denote quantity here quantifiers. These statements also have words that denote categories or kinds of things, right? Like Canadians and humans. These are our category terms, right? And then there are more physicists, people who are smart, etc. So we're looking at quantified categorical statements. Quantified, meaning that they contain a word or phrase that denotes quantity, like all, most, or 37.3%. They're categorical because they contain a word or phrase denoting a kind of thing. Actually, they contain two, like Canadians or battles in World War II. And finally, they are statements because they're a bit of language that can be true or false. That takes us all the way back to our very first definition of a statement. A statement is a kind of thing that can be true or false. And these are ones that contain quantifiers and categories. So the first batch of exercises just asks you to identify the basic parts of quantified categorical statements. Some of the examples that you're going to look at are really simple. In these cases, everything is going to be explicit in the sentence and represented by an individual word or phrase. So in the statement, some Americans are doctors, the quantifier is some. The first category is what we call the subject term, and in this case, that is Americans. Then there's what we call copula, which is a form of the verb to be. And in almost all the cases we're going to look at, that form is going to be are. It might be the singular is, but mostly it's going to be are. The copula is just something that glues together the subject term and the second category in the statement, which we call the predicate term. So in this case, the second category is doctors. The only thing you have to worry about are some tricky cases, because what we're doing here is we're standardizing English, which has all sorts of irregularities in it, and we're creating a more rigorous form. So if we were in the formal logic class, a whole bunch of time would be spent standardizing different kinds of English sentences into a standardized sentence that could be used for formal logic. But here we're just going to do a little bit of standardization to indicate the range of sentences that can be treated using the kinds of tools we're talking about. So consider this sentence. 30% of Canadians speak French. So what's the quantifier here? 30%. That's easy enough. What's the subject term? Canadians. Again, easy enough. But we don't have a copula, and we don't have a predicate term. Instead, we have this verb phrase, speak French. Now you remember always have to have two categories and these categories are always defined by noun phrases. So what we want to do is change the verb phrase here into something that into a noun phrase so that we can talk about the quantified relationship between two categories. So what we're going to do is we're going to say that the copula is implicit and the predicate term is people who speak French. And in general, what's going on with this kind of situation is that we're going to take this verb phrase and we're going to add people or things in front of it to turn it into a noun phrase. So the basic lesson, sometimes the copula is implicit and sometimes the predicate must be turned into a noun phrase. Okay, but before we go on to talk about the argument schemes for inductive generalization and instantiation syllogism, I just want to run through a few of the homework problems on quantified categorical statements. So here's the sample problem. The sentence is some dinosaurs had feathers, right? So here we go. The quantifier is straightforward. It's some, right? That's easy. The subject term is straightforward. It's dinosaurs. Again, though, we get to this thing where rather than having an copula and a noun phrase, we have a verb phrase, had feathers. So we change that to saying that the copula is implicit and the predicate terms is things that had feathers. Okay, now let's just hit a few from the problem set itself. Some politicians are not members of tennis clubs. Again, the start of this should be easy. The first two, I mean, for all these, it's like quantifier is the first term, because I'm not doing tricky problems here. And the subject term is the second word, right? Some politicians. So now you have to ask, is there a copula here? Yes, there is. Are is a copula. Now, the predicate says not members of tennis clubs. We need that to be a proper category phrase. So we can change that just to make it smoother to people who are not members of tennis clubs, something like that, right? All dogs go to heaven. Again, it starts easy. All and dogs. Now we've got go to heaven. Go to heaven is a verb phrase. There's no, it doesn't say is or are here. So we want to say that the copula is implicit. And the predicate term we need to rewrite. We can say things that go to heaven or animals that go to heaven. I use things as sort of the most generic term possible. So, yeah. Okay. Next one actually is a little tricky up front. Most is the quantifier. At this point, a lot of people are tempted to just say things, but look at where the copula is. Copula is after fridge. So the subject term is all of things in the fridge are, and moldy is an adjective. We want to make it a noun. So things that are moldy. Some birds do not fly. This works just like all dogs go to heaven. So some birds, implicit, things that fly. Or we could say animals that fly. Either way. So those are quantified categorical statements, which are the most basic elements in making generalizations. I just want to introduce three more terms for talking about quantified categorical statements, and these will hook up what we're doing with statistics. But don't worry, we're not going to go really into statistics into this class. I'm just going to be borrowing a few terms so that what we do here is compatible with statistical science. And the bits of vocabulary I want to talk about are population, variable, and value. So a population is just a group of things with a property. So the predicate term, the subject term, these are going to define populations. When we talk about populations or terms, we're going to replace those terms with variables, right? And a variable here is just like what it is in mathematics. It's an abstract term that can take different values, right? And then these values would represent different populations. So, and the values are just the different forms a variable can take. So let me make this more concrete with an example. 30% of Canadians are people who can speak French, right? Canadians, people who can speak French, those are both populations, right? We're going to replace those sometimes with variables. So we're going to say 30% of Fs are G, and typically F and G are the two variables we use for the subject term and the predicate term. And we can imagine these variables then taking other values. So if the variable is F, it was Canadians, but it could also wind up being Americans or people from Mexico or whatever. And then the G's, the G originally was people who speak French, but it could also be people who speak English, people who speak Spanish, right? And so we're just bringing in some language of mathematics here to talk about subject and predicate and hook up what we're doing with standard terminology in statistics. So let me give you one more example, and then we will move on to talk about inductive generalization. Here's a sentence I use frequently in my ethics class. Funnily enough, we talk about statistics in my ethics class, because if you want to understand a social problem, you have to bring in some social science, right? And in my ethics class, one thing we talk about is housing and eviction. So here's a statement. 1 in 8 Milwaukee renters have experienced a forced move. It's a quantified categorical statement from a sociological study of eviction in Milwaukee. So what's our quantifier? 1 in 8. The copula is, so the subject term is Milwaukee renters. So that's the subject term. We will use the variable F for it. The copula is implicit, and the predicate term is people who have experienced a forced move. So predicate term becomes our G. So we can replace Milwaukee renters with the variable F, and then that will have two possible values, yes and no. Are you a Milwaukee renter or not? And then the G is people who have experienced a forced move, and the values that can take are yes and no. Okay, so now there are two styles of argument that involve these statements that we've just been studying, quantified categorical statements, inductive generalization, and instantiation syllogism. And in this class, we're going to be talking about inductive generalization. This is essentially the cases where you move from statements about a sample to statements about a whole population. So you've got a the big quantified categorical statement is in the conclusion. But let's just go into that. Let's take a look at that. So this is section 2, inductive generalization. Again, we've got a population, which is a group of things with a property. And in an inductive generalization, this is going to be this is the larger group of things that you want to draw a conclusion about. The population is going to be in the conclusion. The other term we need is a sample. A sample is any subset of the population, right? And in an inductive generalization, The sample is the smaller group of individuals that appears in the premises, right? So generalizations move from samples to populations, right? So an inductive generalization, we can define it as an inductive argument with a quantified categorical statement in the conclusion and a quantified categorical statement about a sample of that population in the premises. So there are two quantified categorical statements often. One's in the premises and one's in the conclusion. The one that is about the bigger category, if that's in the conclusion, you're making a generalization because you're moving from a sample to a larger category. And if some of the language around this appears messy, I'm moving from a different way of analyzing it, which I picked up from a previous co-author, to this way of doing it, which is simpler. So, and more in line with things, with the way people talk when they don't have degrees in philosophy. But in general, the idea is still the same here. We're starting with particulars, we move to a generalization. So this becomes the argumentation scheme. In a sample of things with the property F, X% of them also have the property G. Conclusion, in the whole population of F's, roughly X% are G. Right? And then, so what we're doing is we're moving from a premise that's about a small group to a conclusion that's about a large group. So, whenever you encounter an argument, I'm just reiterating the basics, we want to ask, are the premises true? Do the premises support the conclusion? And is there any information that's missing? With, do I need to hit all of this? Yeah, I'm going to skip this. With inductive generalization, we want to focus on two questions that we need to use to decide whether the premises would support the conclusion. Is the sample large enough? And is the sample representative? This is where we get into the language of statistics. So, one thing that happens here that's important to realize is once you start applying levels of statistical rigor to generalizations, pretty much any generalization you draw in the course of ordinary experience is going to be weak, right? And so one thing we have to think about is, because we're always making generalizations based on ordinary experience, we couldn't walk through the world without it. We need to think about, again, actually lowering our standards of evidence from even statistical significance. With a lot of argumentation schemes, there's a fallacy that goes with the argumentation scheme, and the fallacy is the name of the bad form of the argument. If I teach a full unit that's just about fallacies, I say every fallacy is the evil twin of a good argument, right? So with a generalization, the evil twin of an inductive generalization is a hasty generalization, right? So it's a fallacy that is committed when you make a generalization based on a sample that is small or biased. Okay. One of the things that you have to do in the exercises is assess inductive generalizations. So in order to do this, we need to know some of the language of for understanding populations and sampling. A margin of error. This is a phrase we hear a lot. If you listen to the news, anytime a poll comes up, they will mention margins of error. It's important to know what it is and it isn't. So the technical definition is it's a range around the frequency of a trait, that is the quantity of a variable, in a sample such that we can be 95% sure that the overall population is in that range. So when you move from a sample to a population, if you want to be 95% sure of your generalization, you need to add this margin of error, right? This is a purely mathematical property that is a relationship between the size of the sample and the size of the population. And it is assuming that the sample is random, right? So even when you see a poll that says, oh, clearly Biden is going to win, his lead is well outside the margin of error, there are still other ways it can go wrong, right? The margin of error does not take into account, for instance, sampling method. In the other reading I had you do from Southworth and Sawyer, which is the book that we're going to be using for a lot of the stuff on cognitive bias, they talk about the old-fashioned method of survey sampling, random number dialing, right? You just dial numbers at random, and once upon a time, within my memory, random number dialing was a reliable way to get a random sample because people picked up the phone for random numbers. There wasn't a distinction between cell phones and landlines. Everyone had a landline. You were picking up a landline, you'd pick it up no matter who rang, you'd probably answer a question. In the cell phone era, the random number dialing is just not as reliable anymore. None of that would be taken into account in calculating margin of error. Margin of error is just about the mathematical relationship between the sample and the overall population. So I just want to give you a few, this slide just mentions what I just talked about. But I want to give you a few rules of thumb that are useful for evaluating sampling when you see it like in a newspaper. Either the two I encounter most are political polling and health news about there's a new cure for bad breath or whatever. Given a certain set of assumptions, the margin of error always falls in a certain range. So if you have more than 50,000 individuals in your population, the sample size you need levels off. I don't have a graph of the curve here, but if you're trying to guess something about more than 50,000 individuals, you're not going to get much more benefit from larger samples. The other thing is that if sampling size is easier to guess, if you know that the samples is close to 50-50, given those two assumptions, we can say that a sample of 1,000 individuals gives us a plus or minus 3% margin of error, right? Am I doing this right? I hope so. And this is what most statistical surveys, most political surveys shoot for, right? So here's the population size. With a population of 50, to get a sample of plus or minus 3%, you basically need to sample everyone, right? But after a while, as the population gets bigger, the number of people you need to sample levels off, and it doesn't do you any more good. So for the larger populations, if you're trying to make an inference about, for instance, all of America, having a large sample becomes less important than having a representative sample. And the classic example that's brought up in Southworth and Sawyer is the 1934 presidential election. I hope I'm getting the date right. But it was FDR versus Alf Landon. And a very large survey concluded that FDR would lose in a landslide. But the survey was based on, I believe, car registrations. And in the 1930s, you had to be pretty wealthy to have a car. So even though it was a larger sample, it was a biased sample. A young pollster named George Gallup did a sample that was only like 1,000 or maybe 3,000 people, but it was genuinely random. And he correctly predicted the outcome of the election. And so this is often now used as a kind of parable for the importance of genuinely random sampling. All right. So, like I said, for large populations, getting enough people isn't as important. Well, you reach a space of diminishing returns for large samples, and what you really need is a genuinely representative sample. So these are some things to be on the lookout for when you're looking at sampling methods. A genuinely random sample is what you want. A genuinely random sample means that each member of the population has an equal chance of being in the sample. A lot of times, even in science, rigorous published science, you don't get genuinely random samples. Often getting genuinely random samples for human beings would be unethical. You would, for instance, have to randomly give people disease, which has been done, and has been done by American doctors. Now I'm getting off into my bioethics course. In the Philippines, in the early 20th century, American doctors conducted highly unethical experiments on prisoners. Well, that amounted to giving people diseases at random. But generally, you're not supposed to do that. And there are plenty of other examples of unethical experimentation in the history of American medicine. But generally, there are two other kinds of samples that you will encounter. A self-selected sample is a sample in which people choose to be in the sample. You put out an advertisement that says, here, come talk to me, engage in this experiment. Self-selected samples have very particular biases. They tend to overrepresent outliers. Anytime you have a web poll, you're dealing with a self-selected sample. People have to choose to click on your poll. People tend to choose to click on polls when they have, for instance, strong opinions, right? So if you're doing political polling, people with strong opinions in any direction will be overrepresented for a self-selected sample. Another place this comes up is with sex surveys. Almost every sex survey uses a self-selected sample because people don't like to talk to strangers about sex. So who is willing to talk to a total stranger about sex? Well, actually, it turns out people with unusual sexual practices. So actually, what's a good phrase here? I'll just say, people
with sexual practices that aren't represented in mainstream media tend to be overrepresented in sex surveys. This goes all the way back to the 1950s with the Kinsey report. Okay. Sample of convenience. This is a sample of individuals that happen to be accessible to the researcher. This is the most common kind of sampling in psychology. Most psych tests, well, things have probably changed in the internet era, but for the longest time, most psychological testing was conducted on freshmen in intro to psych classes because they were accessible to the experimenter. Notice that freshmen in intro to psych classes are not representative of the overall population. Young people, 18 to 22, generally from wealthier backgrounds. Bunch of things like that. Another one that comes up is all the patients in a certain hospital, right? I'm just sampling the people that happen to come into the emergency room in LA or wherever. One final kind of sample I want you to be aware of is what's called a stratified sample. A stratified sample is a way, when you can't get a completely random sample, to try and approximate it. And so what happens is you divide the population into specific subgroups to ensure that those subgroups are represented properly. So in the Milwaukee area renters study, which gave the statistics about eviction for Milwaukee that I use, what the researchers did is they identified majority black and majority white neighborhoods, and then balanced the number of black and white neighborhoods to match the overall distribution of the overall population for the city, right? This way they're ensuring that that value is adequately represented. And then within those, once they identified neighborhoods, they picked blocks at random and surveyed everyone in that block. It's not a fully random sample, but it is as close as you can get in many circumstances. And a stratified sample, most of the time, is going to be a better sample than a self-selected sample or a sample of convenience, which have known biases. Right? All right, so the next set of homework problems asks you to look at inductive generalizations, put them in standard form, and I needed to update the phrasing on the question here, because it mentions things like warrants. Don't worry about that. Just put it in standard form for a inductive generalization, and then ask the two crucial questions. Is the sample large enough? And is the sample representative? Just using the rough tools that I've given you so far. Pair up in groups and talk about your answers, and then we'll go over them together.
Okay, let's just take a look at a couple problems from the next section before we go on to talk about instantiation syllogism. So for these, you needed to put the argument in standard form for inductive generalization, and then discuss the size of the sample and the representativeness of the sample. And in the example here, I've got it done. I do all of the standard forms with two premises, which is a bit more complicated than the version of inductive generalization that I'm giving in the current PowerPoint. So I'm going to show you how to do it two ways. And it's kind of a trivial difference, and you would get credit for doing things either way. So let's just start here. On December 1st, 2005, a phone-in poll of 404 Fox News viewers found that 87% believed that schools, courthouses, and other government buildings should be allowed to display Christian Christmas imagery. We can conclude, therefore, that about 87% of all Fox News viewers believe this. So the way that I used to do this and the way that it's done on the answer sheet is with two premises, and it's the first premise would just look like this. In 404 cases, the property of being a Fox News viewer was present, and then in 87% of those cases, the property supporting public displays of Christmas imagery was present. And then, so this, putting it this way, forces you to identify the two separate properties that are part of the quantified categorical statement, right? Your F property and your G property. And then the conclusion would be that 87% of Fox News viewers support the display of Christmas imagery now on government buildings. Now, one important thing to see here is that this conclusion is just about Fox News viewers, right? When you're analyzing whether the sample is biased, you might say, well, it's a sample of Fox News viewers, so that doesn't represent the country as a whole. It's a biased sample, which is true. But the conclusion is also about Fox News viewers. So simply the fact that they polled Fox News viewers is not enough to make it to make it biased, right? Because you've got the same you've got the same group in the premises and the conclusion. Now, actually, the way I want to start people to start doing this is just with one premise, which will make things simpler. So what you could do is you could say, in a sample of 404 Fox News viewers, 87% supported hang on. 87% supported Christmas imagery on government buildings. And then the conclusion can be, therefore, in the whole population of Fox News viewers, 87% support. Right, whoops. And here, let's make this pretty. And we'll move the line down too. I'm taking up your video time being finicky. There. That's a shorter version of it. And that emphasizes the idea that in a inductive generalization, you're moving from a sample to a population, right? All right, so now we want to assess the size of the sample and the representativeness of the sample. The size of the sample is 404 viewers, and that's pretty small. The thing you want to look at here is this PowerPoint slide. So when you're dealing with populations of over 50,000, and there are millions of Fox News viewers, you can use these rule of thumb. You can use this rule of thumb for margins of error. 500 people will give you plus or minus 5%. Most political polls shoot for plus or minus 3%. This is less than 500, so that's pretty mediocre, right? And the representativeness, like as I said before, the sample is of Fox News viewers, but the conclusion is also about Fox News viewers, so that's not a problem. The problem is that it's a phone-in poll. That means it's a self-selected sample. Self-selected samples overrepresent people who are, in politics, politically radical. In general, they represent outliers, overrepresent outliers. Okay, for the next one, we have a case of ordinary reasoning, and it highlights again the fact that everyday reasoning never rises to the level of statistical significance. So this is a person who has two dates with men. They are both dates are very handsy, and she concludes that men only want sex. So you could do it with two premises if you're following the example I gave. In two cases, the property being a man was present. That's your F. In 100% of those cases, the property of only wanting sex was present. That's your G. Conclusion, men only want sex. If you do this as a single premise, it's going to look like this. In a sample of two men, 100% only wanted sex, right? And then the rest would just follow from there. And again, this one's pretty straightforward. It's clear that this is not a representative sample. The sample size is minuscule, and the sample was selected. It's not quite a self-selected sample. It's selected by the person speaking and the person who chooses to date the person speaking, right? So the sample is the people she chose to date and who also chose to date her, and therefore is not representative. It's pretty straightforward.